Welcome. This is the 8th video in the series Patterns Among the Primes. In this video, we apply the work we've done to the study of expected biases in the last digits of consecutive primes. In 2016, Lemke Oliver and Soundararajan published a study of the first 100 million primes and reported a bias compared to what they would expect from just looking at ordered pairs of last digits. This was picked up in the popular press. Here's the table from Lemke Oliver and Soundararajan's paper. Over the first 100 million primes, they tabulated the last digit of a prime versus the last digit b of the next prime. And so a prime ends in a 1, the next prime ends in a 1, they add that to that first row of the table. And when they looked at this table, they thought, well, shouldn't all ordered pairs be equal? Shouldn't there be 6,250,000 of each? And if so, we're observing large deviations in the table from that score. In this video, what we'll show is that the observed biases are entirely expected. Further, we'll show that the biases will vanish, there will be equalization, but this will happen far, far beyond the computational range, well beyond anything we would be able to exhaustively study. For a starting point, we have these models of the relative populations for gaps in the cycles of gaps across stages of Eratosthenes' sieve. These models start over on the right-hand side. We used initial prime 37 to get our initial populations. As the primes continue out to infinity, the system parameter lambda goes very slowly to 0. The first 100 million primes occur by the mark shown there around lambda equals 0.348. You can see this work developed in videos 2, 3, and 4 of this series. The other piece that we'll rely on is the intervals of survival. This was the subject of video number 5. And so the interval of survival, if we take a cycle of gaps for pk, the interval of survival is that interval from pk squared to pk plus 1 squared. And what we've seen is that the distribution of gaps in that interval of survival agrees to first order with the relative populations of gaps at that point in the sieve. So how do we get from last digits to gaps? Consider a prime that ends in a 1, and suppose the next prime also ends in a 1. Then the gap between these two primes must have been 10 or 20 or 30 or 40 or 50, some gap congruent to 0 mod 10. The other pairs of last digits that would have this set of gaps would be 337799. If we have any of these digits for the last digits of consecutive primes, the gap must have been 0 mod 10. If we have a prime that ends in a 1 and the next prime ends in a 3, then the gap must have been 2, 12, 22, 32, 42, some gap congruent to 2 mod 10. There are two other ordered pairs of last digits that would fall into this team. Similarly for 4, similarly for team 6, and for team 8. So the ordered pairs of last digits fall naturally into teams based on the residue mod 10 of the gaps. Here are the counts over the first 100 million primes for the different teams. And we see that team 2 has a lead over 22 going on 23 million. Prime pairs fall on team 2. Team 0 and team 8 are lagging. And then team 6 is close. Team 4 right in the middle of the pack. What would we expect these scores to be? How many occurrences would we expect to to have occurred on these teams. Well, if we look over at the ordered pairs, there are 4 ordered pairs on team 0, mod 10, and then 3 ordered pairs on each of the other 4 teams. So all things being equal, we would expect team 0 mod 10 to have 25 million prime pairs associated with it at this point through the first 100 million gaps. We would expect every other team to have around 18.75 million. And that's where we notice this discrepancy. But this is a little bit of misdirection. What if we instead look at the gaps that are required to produce those ordered pairs? What would we expect from the gaps at this point through the first 100 million primes? Well, when you went back to that family of curves, the relative populations, and we show that mark, if we stop and look at that section for a second, the gap 6 is way up top, and then 12, 10, 18 are crossing over 2 and 4 right there at 1. There's a handful of gaps around 3/4. Many of the other gaps have barely gotten off to a start. If we accumulate the first 108 million gaps between prime numbers, we get this distribution. We see that the distributions of the first 108 million prime gaps closely follow the relative populations, that section shown over there at the left, that the peaks are where we would expect them to be. If we take that noisy family of gaps and just pull out who are the members on team 0, mod 10, and we see that it has 10, which is crossing over 1, and then 30 and 20 are the next two. They're around a half. Everybody else is smaller at this point through the first 100 million prime numbers. Keep your eyes on the left side of the graph. We have this Polignac result that every even number arises as a gap in the cycle of gaps, and we can calculate its asymptotic value. We cannot develop the full model without sampling initial conditions in an appropriately large corresponding cycle, but we can always calculate the asymptotic value. And so you'll see that the gaps on team 0 mod 10, they're showing at 0.35 is well below where they're going to be at infinity, right, as primes get larger. Here's team 2. Its strongest member is the gap 12, which over the first 100 million primes is crossing over 1.25 in a relative weight. And then it has the gap 2 itself, which just keeps contributing a score of 1. And then the other members fall below there. Gap 22 is getting close to a half. On team 4, its best member is the gap 4 at this point, and that's a contribution of 1. The gaps 24 and 14 are showing pretty well here, coming up on 3/4. Everybody else on their team at this point is still pretty low, down below 1/4. Team 6 has the most populous gap in the cycle. Here's gap 6 itself, and it's already cresting a score of 1.75. The other members on its team are at 0.5 or lower. And then team 8, represented well by 18 and then by 8 itself. But each of those are barely at 1. They haven't even reached 1 yet. How do we look at these in aggregate? We add up the scores for all of the members of the team up to some maximum gap. So we use the gap 60. So if you take all the gaps from 2 to 60 and divide them up on their respective teams, modulo 10, then we divide by the score for team number 2, just to keep things nice and clean. So this is what the curves look like. We have The score for Team 2, Mod 10, right up top, constant score of 1 by design. Team number 6, over there on the right-hand side, started a little ahead of Team 2 and now is sagged down as the sieve continues, even though it has the most populous gap 6. The rest of its team are laggards. Team 4 coming up there in third place. Teams 8 and 10, they just don't get off to a strong start. But if we look out here to the left, we will see that over on the left, Team 10 is going to zoom past the other ones at some point in the evolution of these populations. But for right now, we're going to look at that section where they're crossing around 0.35. The working hypothesis here is that the gaps in the interval of survival are an approximately uniform sampling of gaps in the corresponding cycle of gaps. The perceived bias would require that the sample would show up the way the circles are laid out, that somehow we would get as many 2, 4, 6, and 8 all there at level 1, and that somehow the Team 0 Mod 10 would show up 4/3 as often. And that's astounding. How could we possibly get that? There just aren't, it would be a highly skewed sample from the population. Highly skewed. Let's put it on a scoreboard. So here's the observed bias. We lay out the teams, and then that first column are the scores through the first 100 million primes as tabulated by Lemke Oliver and Soundararajan. That next column shown are the estimates just based on the number of ordered pairs on that team. Right, so the Team 0 had 4 ordered pairs and the rest of the teams had 3 ordered pairs. This is the observed bias in 2016. If we insert the scores at this point through max gap 60 and at this section for 100 million primes, we see that the occurrences, the statistical occurrences, are well in alignment with what we would expect, and that the bias is not a surprise. On the other hand, those estimates based on the ordered pairs, on the assumption that all ordered pairs occur equally often, that aligns well with the asymptotic values. If we let these curves up through max gap 60 run out for primes through infinity, we see that a lot of that perceived bias has been erased. We're in strong agreement with the estimate. And if we let that max gap go further, out to say 2310, we have almost completely erased any bias away from that naive estimate based on ordered pairs. And a reminder here, we can calculate the asymptotic values without having the full models. So we can extend Gmax here at infinity, and we are unable to extend the max gap for these samples. So what about larger gaps for the samples? We only have models up to 82. Are we missing some larger gaps jumping in and changing the relative scores? And the answer is no. We can model the proportion rho of the modeled gaps out of the total gap population at that stage of the sieve. And we see that through the first 100 million primes, the proportion rho is over 97% of all gaps are represented by the gaps we've modeled. And we see that over the next several orders of magnitude of prime numbers, that proportion will remain above 90%. In fact, as we get over to the computational horizon, the gaps we have already modeled will still represent 80% or more of the total gaps. This study has forced us to distinguish between the prime numbers we know and love compared to the prime numbers we could substantially sample statistically, and then compared to the primes in the very, very large. This study of last gaps just takes us right to these distinctions. Returning to the models, from Merton's third theorem, we see that in order to cut the value of lambda in half, we have to move to primes about the square of the current prime. And so we've seen that around 0.35, we're working with primes around 42,000. To get down to 0.25, we have to work with prime numbers around 3 million. To get down to 0.15, we're working with 11-digit primes. Notice how still early in the evolution of many of these small gaps we still are. 30 has still not become the most populous gap. Let's zoom in on that left-hand side of this graph. To get down to 0.1, we need to be working with 17-digit primes. 30 doesn't become the most populous gap until we're working with 21-digit primes. And then way over there, when the models of these small gaps finally start sorting out, over there at 0.01 to drive lambda down to that point, we're talking about the cycles for 163-digit primes, far beyond what we could compute. Here's what we've shown. The last digits of consecutive primes up through p squared exhibit the bias expected by these team scores, by the relative populations of gaps. And under uniform sampling from the cycles of gaps, this bias vanishes among very large primes. But this will happen far beyond the computational horizon. Thank you.